Oh, it's not moving. Moving. Yes, all good. Okay.
Okay, our next speaker is Azeef. He will talk for the partial symmetry, partitions, and matrices.
Thank you. Thanks, Mengfan, and thanks, Joe, for a very nice introduction to partial symmetry and inverse semigroup. So that's probably half of my talk already taken care of. Anyways, so I'll be talking about partitions and matrices. Let's start off with inverse semigroups. So it's joint work with James. Like, the picture was taken on my first week in Sydney, like 3-4 years ago. And the talk, I'm not going to, pardon me, good, thanks. So the talk, I will not go into much mathematics. I'll try to keep it very gentle. And it's roughly about how the last 3-4 years, the work we have done and how things stand. It's like an overview about the whole thing. It's been a very fruitful 3-4 years. We have had some very nice papers. So the talk, a major part of the talk will be about this paper, which was our first paper together. I'll tangentially touch a few of these, like the 4th one and the 6th one will appear in the course of the talk. And I'll end with star regular semigroups, which deals with matrices, and see how things are there. So starting in the talk, as I said, I'll talk about how inverse, not how, but just I'll introduce what are inverse semigroups and why they are nice objects. And another way of looking at these semigroups is to see them as groupoids, which is actually the statement of ESN theorem. I'll take you through the theorem, and then broadening this notion of partial symmetry will lead us to more general classes of semigroups, which are the two classes which I'll primarily focus on, regular star and star regular. They're supposed to be in color. And I'll tell you how and why these semigroups are also groupoids. And when I say these are groupoids, what I mean is you can see these objects as exactly as groupoids. There are two ways of seeing these things. One way you see them as a full operation, like a semigroup, and the other one is you break up the binary operation into a partial operation. And it's exactly the same, like what we have is a category isomorphism, so you're not losing anything at all. So yeah, it's fair to say that semigroups are groupoids in this context. In the process, you'll see symmetric group and some semigroups. Some popular ones. Symmetric inverse monoid is the one which Cho talked about in the beginning. So it is the semigroup of partial bijections. Full transformation monoid is the semigroup or the monoid of all mappings on a given set. Partition monoid is slightly more general, which I think a majority of you already has encountered more than once. And finally, we'll see the full matrix monoids over complex numbers. And some groupoids. And the good news for today is, yeah, tiny little people, we like to keep n as 3. So S3, I3, P3, 3x3 matrices. Simple. So, I missed a picture here. I don't know where it went. So there was a picture here, which is a very beautiful picture of Sydney Harbour Bridge. I don't know. Anyways, so groups model symmetry. I think everybody knows that. And introducing some notations, this is how we like to see symmetry group for the day, for the next 40 minutes. So this is an idempotent, this is the identity element. So this one maps 1 to 2, 2 to 3, 3 to 1. So that's your 3 cycle, and these are your transpositions. This is how we see S3. These are bijections with 3 transversals, like 3 lines crossing across. And as I said, like there is an alternate way of seeing the same thing. You can see it as a groupoid with a single object where you see each element as now as a morphism or an arrow from the object to itself. And you can see that there are 2 generators for this, and that's a nice way of seeing it. And in the case of groups, there doesn't, it doesn't say anything profound. It's just another way of saying it. All are nice, good, everything works. Now we move on to the definition of a groupoid. A groupoid is essentially a small category where every morphism is invertible. And if you compare it with the previous picture, you realize that you're actually just pulling things apart. Now you have more freedom in moving around. And when you have a morphism from, say, A to B and another morphism from B to C, you can compose them from morphism from A to C. There are these nice identity morphism on each object. There are inverses, and it's all nice enough, and but it's not quite a group. And the most popular groupoid is a group which is you splash all these objects together and you get a group. So this is a groupoid, and this is the joke which won the best joke award at AAC 06, if I'm not wrong. So it was actually Roosbay's caption. Went with I have not included just Roosbay's caption. Roosbay's caption was a groupoid is a group on an opioid or something like that. So so this was the AIC certified version of the folklore joke. Now we also have partial symmetries, contractions, inflation. So the first picture was supposed to be Harbour Bridge, and this is now Opera House. So that's how it works. Anyways, so we need semigroups because partial symmetries, contractions, inflations. And semigroup is a very simple object. It's a set along with an associative binary operation. But one of the biggest criticisms is semigroups are too general to be interesting, which is true. So, for instance, there are way too many semigroups of order 6, whereas you have just a couple of groups. Anyway, that's one reason why we focus on semigroups having group-like properties. And by group-like properties, we mean the existence of inverses or some kind of inverses. And that leads us to these classes of semigroups. So of course you have groups, which is a semigroup. Then you have inverse semigroups, and the prototypical example is partial bijections. We have more general class of semigroups called regular star semigroup, where you still have your involution and your inverses, generalized inverses, interacting in a very nice way. You go further, the interaction becomes deeper. Then you have your star regular, and even that has a very nice class, which is this matrices. And then you have regular semigroups, which is the prototypical example is the full transformation monoid, which is the semigroup of all mappings. And then you can go to bind semigroups like binary all binary operations on a binary relations on a finite set. So today we'll be focusing on these two classes, regular star and star regular. And so first of all, what brings you closer is, as I said, it's the notion of an inverse. You can call it a generalized inverse. So an element is said to be inverse if it has something bringing it back. So ABA is A and BAB is B. So then we call B to be an inverse of A. And the semigroup S is said to be an inverse semigroup if it has a unique inverse. So you're insisting that there is one element and just one of those. So they arose from study of pseudo groups at the early 50s, 40s, whatever. And they were introduced independently by Wagner, who was a Russian mathematician, and Preston, who was at that time in UK, if I'm not wrong. And later on, he relocated to Monash. Symmetric inverse monoid is the, as I said, is the semigroup of all partial bijections on a set X. Now, how do you compose two elements in semigroup in a symmetric inverse monoid? We'll continue with this diagrammatic thing. So here, if you take an element A, the A inverse, which is actually, we are noting it by A star also, it's actually the flipping of this object. And how do you compose them? You just keep them together. Now you see that 1 will go to 1, 2 will go to 2, all good, nice. So you get A inverse, and A inverse A here is 2 goes to 2, 3 goes to 3, that's it. So unlike the case of a group where A inverse A is identity, what we get is A inverse is an idempotent here. This is an idempotent, because multiply it again or you flip it, you get the same thing. So projection to be more precise, but you don't get the same element. So A inverse and A inverse A starts to differ. Now this is the D-class picture of a symmetric inverse monoid generated by gap. So whenever you get a semigroup, every semigroup has such kind of a picture where you can arrange these things in a very nice egg box kind of way, where each of these shaded places represent groups. You have your symmetric group sitting on top. There is a gravity in this picture, like you take any two elements here, when you multiply, either it stays in this box or it falls down. It can't go up. So that's how things work in the semigroup world. And if you focus on the second D class, you see that there is a kind of symmetry there, and you can arrange these green shaded ones, which are our projections, idempotents, which are fixed by flipping. You can arrange them on your lead diagonal, and they form groups. So this is C2, 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 and there is a bijection between different boxes here. These are called edge boxes or edge classes, and it's a very nice symmetric picture. Anyways, so moving on, as I said in the beginning, so there is an alternate solution to the original problem of abstraction of pseudogroups, and it was by Charles Ehresmann, who was a category theorist, actually a geometer, I think. Anyways, he used groupoids, and he said, well, you can model this idea of abstraction of pseudogroups using groupoids. And it was later in 1965, Moore-Schein came up with this idea that you can connect these two ideas by saying, okay, inverse semigroup, any inverse semigroup is same as a groupoid. So it's just two equivalent ways of looking at the very same object. And this was later, so how this works, it's that you start from an inverse semigroup. So as I said at the beginning, every element of an inverse semigroup has a inverse element, so we call it A inverse, and A can be seen as morphisms. So first of all, it follows from basic algebra that A inverse and A inverse A are idempotents. And then you can see each element of your inverse semigroup as a morphism from the object A inverse to A inverse A. So this way, you take an element of your inverse semigroup, it becomes a morphism or an arrow. Now, you take any two of such objects, you can't compose them all the time in the groupoid. You could compose them all the time in the inverse semigroup. But you say that you can compose these two elements only when the range of the first one matches the domain of the second. So you starting from an inverse semigroup, you have a full binary operation. Now you are putting a restriction on that, and you get a new product, which now is a partial associative product. And this remembers only the easy products. So it's the sense that these are the ones which are called the trace products, which fall inside the D class, blah, blah. There is some theory behind that. Anyways, it's essentially the easy products that you compose. And this gives rise to a partial composition, which is associative. And this forms a groupoid because you can also go in the opposite direction because every element has an inverse. And if all this happens, then this will also be the inverse of AB. So this is how you associate a groupoid starting from an inverse semigroup. Now further, you're losing some sort of an information, but that's actually captured by the underlying objects, which is the idempotents now. So this idempotents of an inverse semigroup, it's known that it forms a semilattice under the natural partial order. And so you consider an object set as a semilattice, and the morphisms further respect an order structure of the vertices. So the idea of the groupoid is that there is an order underlying this elements. So you lose your binary operation, but now you say that it comes in the form of an order and the object set being a semilattice. Further, this order says that the morphisms can be restricted and co-restricted. So you get an associated groupoid called the inductive groupoid. So you start from a inverse semigroup, you get an inductive groupoid, and conversely, you can axiomatically define an inductive groupoid using the semilattice and its order structure. And there is a unique associated inverse semigroup, and that's the statement of Ehresmann-Schein-Nambooripad Theorem as Mark Lawson put in his book. So inverse semigroups are isomorphic to inductive groupoids. So on the left-hand side, you have in the category of inverse semigroups, where you have inverse semigroups and homomorphisms between them. And on the right-hand side, we have objects as inductive groupoids and morphisms are now inductive functors. So this is a category isomorphism in the sense that you start from an object, you go there, you come back, you get back the exact same semigroup. So, and it's not very common in the category theory world that you end up with category isomorphisms, but here we do get it because we are not losing anything. So the elements of a semigroup itself becomes the groupoid. So that's something very unique about this construction. Anyways, now let's move on to my hero of the talk. This is a regular star semigroup. So it's a semigroup where now, instead of saying that you have a unique inverse, you accept the fact that the world doesn't work how you want it to be. So you don't no longer have a unique inverse, but then you have a special inverse. So what do you mean by a special inverse? So what I mean is you have this unary operation, which in the case of inverse semigroup was just A going to A inverse, and that was everything was fine. That was the only inverse. But now you're saying that, okay, this involution, so the first two parts tells that the star operation is now an involution. And the third part tells you that the inverse is actually given by that unary operation. Okay, so you have an involution on your semigroup, and that involution itself gives you the inverse element. So this is the definition of a regular star semigroup. And why we cared about it? Well, it's the set of bipartitions on a finite set happens to form partition monoid, and partition monoid is very fancy. A lot of people likes it. It appears in theoretical physics, not theory, blah, blah, phylogenetic trees, and statistical thermodynamics, whatever. Anyways, so in particular, the submonoids also form a regular star semigroup, Brauer and Temperley-Lieb. And all these have been extensively studied in the last few years. And how do you multiply elements in your partition monoid? So you take two elements. Now the elements are no longer restricted. Like you can take any sort of diagram, any sort of combination of these elements, and you put them together. You see what goes where. So these two goes to these two. So that's what you will eventually have, and that's the picture. So that's your AB, that's how you compose elements in your partition monoid. Now, A star is given by flipping, just like in the inverse case, you just flip your diagram, you get your A star, and A star now becomes this, which is an idempotent, and which is invariant under flipping. So it's a projection. So A star is now a projection. And A star A is that. But unfortunately, I think I forgot, should have added that. The thing is A star and A star A need not necessarily commute in the partition monoid. So this is the, I can't see the colors there. There is color. Anyway, so this is the how projections arise in a partition monoid. Anyway, now we move to the similar picture of the second D class, which is the bipartitions with two transversals. This is how it looks like. So again, we can arrange these projections in your leading diagonal, all nice green ones. But then you have these yellow ones also. So these are basically the idempotents. So you multiply it with themselves, you get back the same element, but you don't get back the same element when you flip them. So these are additional idempotents appearing at various other places. If you stare at it a bit longer, this part, the top left part, is actually the exact copy of the symmetric inverse monoid, which I showed earlier. Now this bottom left part is actually a reflection of that, which is actually a dual symmetric inverse monoid. And this left part on top is all mappings on a two-element set with two transversals. So it's the part of your full transformation monoid. And this part is actually an opposite of that part. So this is a very still symmetric picture you have about the bipartitions of with two transversals which appear in your partition monoid. And if you look at, if you go back and see it, this is how the D-class picture looks. The D-class picture now has still squares. You can arrange things on the leading diagonal. Here it's not arranged, but we can. You have symmetric inverse monoid, full, what's it called? Symmetric groups sitting on top. These groups here are C2, still fine. Here you have the trivial groups in the bottom D classes. Still a symmetric picture, but then you're sort of losing the symmetry. It becomes less and less symmetric. Anyway, as I mentioned, the ultimate or the overarching aim of the talk is to say that, okay, now you have regular star semigroups sitting between inverse and regular. Are they also groupoids? And that's what we proved in our 24 paper. We showed that they are in fact groupoids, but you have to look at certain groupoids. A bit additional structure has to be provided, and that's what we call as change projection groupoids. Now I'll tell you in the next few slides how this works. So you start from a regular star semigroup, you do the same thing. The crucial role here is played by the set of projections. And given a projection, you take any other projection, you see that PQP is another projection. So this gives some sort of a unary operation on your set P. So you take for each P, it gives a unary operation. So you take any other Q, PQP will always be a projection. So you get a collection of unary operations. And this structure, it so happens this was already looked upon by people in the 80s. So it's called as a projection algebra. So you have a set P, which is just a set, and then you have a collection of unary operations based on the set, and it satisfies some natural axioms and it's an idempotent and things like that. This, as I said, this is a practice talk for Melbourne. So I have a Melbourne picture from Gordon Preston's retirement conference. It has quite a few people who are the leading contributors. So in particular, this is Imauka. This was the first time we saw him, right? And this is Nambooripad. This is Gordon Preston. This is John Hovey. Yes. This is Peter Jones. His name will appear later on. David Eastman. Yes.
Near the back. Middle, just to the right of the near the back.
Yeah. So that's David. Yeah. So, and then we have some semigroup gods. Mishawoko, Wiki, yeah, so on. I don't know if I missed. I'm sure I missed someone. This John Wiki, yes. Anyway, so this was some leading contributors in the area. So let's go back to this construction. So you start from a projection algebra, which something which is pretty natural. And then now you look at the groupoid which arises from that, where the elements of your groupoid from two objects P and Q are precisely those elements which have domain P and range Q. So A star is P and A star A is Q. And then you get a partial product out of it, just like in the inverse case. And you're just getting the EC products, just like in the inverse case. And you're just looking at products where A star is B star B. So if the range of A is equal to the domain of B, then only we compose it. It's the same story as in the inverse case. Now, as in the inverse, you have a natural partial order, so it forms an ordered groupoid, and you associate an ordered groupoid with your regular star semigroup. There is no nothing, absolutely nothing new from the inverse case still here. But then, as they say, making something disappear isn't enough. You have to bring it back, and bringing it back invariably is the difficult part of it. So how do you bring it back? So you start with an abstract projection algebra, because Imoca defined it for us. It was very easy. So you start from that. And then you hit a rod blow. You cannot multiply projections any longer, because they have this, what you call it, projection algebra structure. It's not like a semilattice where you can take a meet and do things. So you have to add a new layer of projections here. So we called it CP. It's a layer of P chains. There is a way of connecting these projections, and it forms this layer using a new relationship. We called it as friendship of projections. It wasn't transitive. That was the reason. And you link these two groupoids. So you get a new groupoid out of your P chains, the CP, and you have this groupoid which you start with. You link them using some kind of an evaluation factor. And that's how you come up with a definition for a binary operation. So you have two morphisms which comes from your groupoid. You want to define a new binary operation. So you look at the restriction of your A to this P prime and Q prime and P prime, and then you look at the restriction of B to Q prime, and then there is this evaluation map which will give a morphism, very specific morphism of your groupoid, and then you can define this, because for every such, you take any such P and Q, you can always find a P prime and Q prime with this property. So you start from AB, which were not necessarily composable. Now you do have a binary composition which you can define. Now the problem is, okay, the good thing is it's a full binary composition, but the problem is this has to be associated. Now that's the real tough part of the construction. Or like you'll be in a situation where you have these two expressions where PIs and QIs are very complicated expressions, starting from A, B, and C, and you want these two to be same. And we did a magic. It is associative, and the trick is you start from what we called as the chain projection groupoid. So how does it work? It has some very specific axioms. So the morphisms respect the underlying projection algebra, which was rather, natural to expect. But then you come up with this coherence axiom, which is a very technical one. And if this groupoid satisfies this particular picture, so whenever you take a morphism with this setting, you want these morphisms. So you have this, so there are three morphisms there, and then these, another three morphisms. You want them to be same. So the one is you left restrict, then you put right restrict. The other one is you right restrict, then you left restrict. All this has to fall in place. If it does, then what you have is a chained projection groupoid, which will give you a regular star semigroup, and that gives this main theorem of our paper, which said that the category of regular star semigroups is isomorphic to the category of chained projection functors. So what we did was you start with a regular star semigroup, you break it up into this projection algebra, groupoid, and evaluation map. So I usually say that projection algebra is like the skeleton, the groupoid gives the flesh, and then the evaluation map is the skin, right? It's the outer cover. So that's how we see it. It had some very nice applications. First one was we got a new proof for ESN theorem. The second one was we could construct what we call as fundamental regular star semigroup starting from a projection algebra, which is sort of characterizing the projection algebras like can you build a regular star started from just a projection algebra, which we can. Here, the P isomorphisms of the projection algebra forms a chained projection groupoid. And the third application was the free regular star semigroup over arbitrary projection algebra, where Nick and Bob joined us. And it has been another very fruitful part of this project. Like, it's developed into what John Mackin calls as a cottage industry. So that's how things are. I'm not going to go to this side of the project because I have to move on. So this is the twist. So now,
There's one question. So
yeah.
if you concentrate on the inverse semigroup, your theorem reduces to the previous one.
Yes.
It's exact same.
Exact same. Yeah. It's just that our proof. So if you look at Mark Lawson's book, his proof is some order theoretical proof of the ESN theorem. So ours, we believe, is a bit more straightforward and transparent if we just specialize it from our case. Yeah. So anyways, so now we move on to some more general ones, or like remembering more about partitions. So when I first showed you the multiplication of partitions, I used the same elements, and I told you like these two comes together, and there is a floating component here which you very conveniently forget. So if these comes together, you will have this additional floating components lying here. You'll just say, okay, we just forget that. This goes to this, this goes to this. But now you say, no, we don't want to forget it. We want to remember it. And to remember that, you will have to add an additional parameter here, which remembers the number of floating components and the number of floating components in the second one. Let's start with I and j. And now you say that when you multiply them, you get an additional one. So now your number becomes I plus j plus 1. Okay, so this is like a twist. It's like you're coming up with a new multiplication based on your partitions, and you're remembering more information about the partitions. So now you get a new multiplication out of your partition monoid. And incidentally, this forms a very special case of general twisting, which arises in monoids, which is again a part of this project. We have looked into the more general constructions, which just appeared on Friday, probably Thursday, I think. Yeah, it's appeared on Thursday with the volume number. Yeah. So these twistings appear naturally in a lot of areas. And how would you expect if you can come up with a very nice star operation? You twist it, you compose it, you get A star, but now you realize that your A star is no longer an idempotent because your second component is increasing. So if you look at your A star and you multiply it with again, it becomes 4i plus something. It's no longer an idempotent. So neither is your A star A, because the second component goes on increasing. So I'm the pauses here. The unary operation star is still an involution, but then A star nor A star A are idempotents. And that's because A star is no longer an inverse of A. So that's what is happening here. You get A star, but now A star is not an inverse of A. So your star and inverses used to coincide in group, to coincide in inverse semigroups. Now it's slowly moving apart. Okay, and this asks, like, do you have hope? Well, there is hope. If you look at your new operation, which we denote by dagger, as flipping the element, but now you add a different sort of component on your second position. Now this way you can compose these two, and then your A star now becomes I minus 1 plus this. So it becomes 0. And similarly, A star A, A dagger A is another element, which is again an idempotent. So you are hitting projections with this special inverses, and both A perp and A perp A are indeed projections. And this leads us to the definition of star regular semigroups, where you do have an inverse, you do have an involution, they don't coincide, but then they interact. Okay, so you do have a generalized inverse, and you have projections which are now of the form A perp, and it's what's called as a star regular semigroup. And this is not the prototypical example of a star regular semigroup, it is a full matrix monoid under matrix multiplication. So if you look at the full matrix monoid, then the involution is provided by the transposes, star. And the inverse is what is the Moore-Penrose inverse, which was independently described by Moore, Gerhammer, do you know how to pronounce that? And Penrose. So, for instance, if you just take a matrix, any random matrix, actually pick one from the title page, and you have your star, which is just taking the transpose of that. But then now you can define your A perp, which is your Moore-Penrose inverse. It becomes this. We use MATLAB to calculate that, but it usually use singular value decompositions. And then you get A perp, which is now the domain of A. It's a projection. You can see that this is fixed by star, and also this is an idempotent. And same A perp A is again a idempotent fixed by star. In fact, all the projections arises in this manner for your MNC. Now, every regular star semigroup is star regular, where I said the star and the dagger coincides. More generally, if you start from a regular star bi-ordered set, so bi-ordered set is this structure of idempotents of a semigroup, and you can construct a free object, which was actually the one of the main objects of our project with Nick and Bob. So then you can get your Rigi. Now Rigi is not regular star, but now it becomes star regular. More exotically, certain things are star regular, abelian variety endomorphisms on a polarized abelian variety, whatever that means, I don't know. But it is star regular by one of recent papers which appeared in one of the French journals. Now we go back to our business. We wanted to construct the ESN, like can we see them as groupoids? So you start from a projection. Now, as I said, star and dagger coincides in the star regular case, so that this becomes QPQ. But now you don't have that. This is what you have. So you have a PQ per Q. Now that becomes a projection. And that means you can always get a unary operation for each Q on your projection algebra set. So you have a unary operation, you have a projection algebra, they satisfy the first three axioms of our projection algebra, but then it fails P4 and P5. So we tried to solve this. We came up with a complicated axiom, but we have not yet managed to build a proper axiomatization of the projection algebra. So that's one negative point. What do you call it? That's one glitch in the whole thing, glitch in the matrix. So now another, also crucially, it seems that the star regular projection algebras, it may not uniquely determine the idempotent structure. So if you look at the regular star case, if you start from a projection algebra of a regular star semigroup, you do get a definitive idempotent structure. And they were, we even showed that they are equivalent as categories in the second advances paper. But here in the more general case of star regular semigroups, it seems that they need not. We don't have a counterexample yet, but it seems that it will not be. In the next 3-4 slides, I'll give an outline of how we still managed to come up with a candidate or a outline for a groupoid construction for this. So it's a work in progress, but what helped us is that the idea of DRC semigroups, which Matthias will be talking in another 5 minutes. So you look at your star regular semigroups, they do form what's called as DRC semigroups, where you can define domain and range operations. So DRC semigroups gives you a setting for looking at just these domain and range operations with some additional conditions. It's an interesting class studied by several people. In particular, we had looked at into it in a recent work. And we have, in fact, showed a category isomorphism there. So we know how to construct a DRC semigroup from a groupoid. So what we looked at is we start from a star regular semigroup. You obtain a symmetric DRC projection algebra. So projection algebras of DRC semigroups was studied by Peter Jones. And on the groupoid side, what you end up with a bi-ordered star groupoid. So the star now is a separate part. It's not part of the groupoid, like in the case of regular star and inverse. In particular, in this case, we see that AB perp is AB dagger is B dagger, A dagger, if this condition holds. Now, this is actually a sufficient condition for this identity of Moore-Penrose inverses to hold. It's, as far as we know, it's not been mentioned in the literature. So you start with this setting, you get a DRC semigroup out of your groupoid. Then you have the star, there's two orders which interacts with each other. And then you sort of infuse star regularity into the construction. So that's how the proof goes. And that's what will lead us to the second theorem, which says that the category of star regular semigroups will be isomorphic to the category of chained bi-ordered groupoids. So this is where things are. We break up the star regular semigroup into its underlying projection algebra, bi-ordered star groupoid, and evaluation map. And another very distinct thing in this case is that the evaluation map becomes sort of less restrictive. It's not connected with the projection strong enough. So that is what is leading to the ambiguity in the idempotent structure. So it's much general. It's so general that you can actually come up with a structure where you have two evaluation maps, but one evaluation map depends on the previous one. Anyway, with this as thing, as I mentioned, we still haven't produced a complete characterization of the projection algebras. We don't know if it exists. We don't know how the projection algebras behave with respect to bi-ordered set. We believe it's quite non-trivial. There is this question of free objects which arise in just like inverse and regular star and star regular. We can also look into various interrelationships which we've been looking in the regular star case recently. So this is where I stop. Thank you for your time, and I hope I have managed to convince you that we need both partial symmetry and symmetry to have a beautiful world.
I'm on page 26.
Definition of was it Moore-Penrose inverse?
Yeah, so it's precisely the I gave you. Yeah. So it's an element which satisfies these four axioms.
But
So
in
there
the
is-
in the case of matrices, like in a concrete example,
Yeah.
what is the
There is no formula for Moore-Penrose inverse. You can calculate them. MATLAB has a inbuilt calculator. So it uses, as I said, it uses singular value decomposition. So you can look at the singular value decomposition, come up with a formula. And that's, I think, exactly what MATLAB does. And so you give it, it will come up with it. So it came from this work in the 50s or whatever, like they came up with this, and it exists and it is unique. So that's so in particular, that's what I was asking James, like this forms a variety if you add in the involution equations also. So. Yeah, so it exists. And it's quite complicated, like we struggled quite a bit like initially to calculate, to see what is Moore-Penrose inverse. Yeah, MATLAB was great.
No